Interesting part is if this is active, why is this not active? And this is one of the major problems that I'm looking at, and this is also one of the major problems that people are actually trying to understand. Most of the textbooks that you read or kids are reading, they say that this is because we are away from the plate boundaries, therefore this area is not active. Therefore, don't worry, there will be absolutely no earthquake. And that is something, I mean, it makes sense to some extent because you can see a lot of earthquakes here. But what doesn't make sense is that why would this be shielded from earthquakes? Okay? And because we know that even on the stable, what they call the tectonically stable areas, we do have earthquakes. And I'll show you an example recently, like an example from India, which is much, much safer than this area because it's a crater. Craters are considered to be extremely stable parts of the planet. But this is not a crater, so we have to consider that it's very hot, it's very young, and there is more energy, therefore there are actually indications that deformation will be there. And this was changed here. Look at that. You got an earthquake in 2015, and you're like, now we just look there. And that has happened every time. You see this tsunami in 2014, you got a tsunami, right? And that changed the whole perspective of the tsunamis. You're like, now there's something called tsunami. It's not like they were like there, it was always, tsunamis are always there. But we have no data. Now we know the data that tsunamis have always been there in that area. Same thing in India, we had a Bhuj earthquake, and then people start working on earthquakes. Okay? We should not wait for a disaster to kick us out and then start working. But unfortunate part is most of the world, this is the case. And here, same thing. So this was repeated just after the earthquake. You'll see many papers coming out now. Because now people are trying to understand what's happening, okay, in this region. And that was something very interesting to know. I'll tell you in a minute what's happening in this area. So the motivation of my talk is just to get an idea about where are we and why is what is happening and why is it happening there. Okay. And these are the major faults. Maybe you've heard about this called Sunda megastrata. We do not call this in geological terms. The whole area is called Sunda land, right? And we talk about plates. We don't talk about boundaries, but for us, whole nation is one. So this is a Sunda plate, and most of the earthquakes are here, and because it's a subduction zone. Similarly, we have this Saran fault. It's a huge strikes fault. We are very active, and we have faults here. We have this fault because here I did not put in this one because I was mainly concentrating on big, huge faults. Okay, and here is the thing that I'll show you in a minute. Now, why I was actually interested in trying to know what's happening here, because everybody was saying it's stable, right? I was like, okay, let me go and check what topography tells me. So this was a clue. The first clue that I got is from plotting these black dots are earthquakes, right? And this, what you see is balls, they're called beach balls, right? They look like beach balls. And they tell you if there's an earthquake, whether that earthquake is operating on what type of fault. Whether it's an active strike slip or thrust or normal, okay? And look at this. Who would have expected a strike slip fault right there in a stable part of the world, right? And it's a strike slip. And it is like, I think I have dates somewhere there. It was like 2010 or something. Very recent. It's a recent data, right? It's not something somebody has created. Even if I consider that there is, there are always errors in the distribution of earthquakes on the top, these are hypocenters. Even if I consider that error bar, it will never be part of any other thing than something happening there. Okay? And that was a clue that I actually tried to understand, okay, what's happening? And you can see that they're almost everywhere. So I'll take you through this island, and the red indicates population density. Okay? The people who are living there, and they will be affected by these earthquakes. That's why this is very important. So this was the image I created just after this earthquake, right? Just looking at the topography and trying to understand. So on a big scale, what was happening? This was an earthquake in 2015. This is a normal earthquake, normal fault, okay, where the block goes down. So this earthquake is active. And the question is that why is it active? Again, this is also not surprising. If you have read about surprising things, don't worry about that because we know Sabah has a historical seismicity going back to the data that we have created as humans. There's a historical data that shows the earthquakes were there. So it was not a surprise. But what is surprising is that you got extension here, compression here. People from oil industry, they will notice there's a lot of very, very good data coming from here. It has beautiful faults. Okay, we have thrusters there. So you have a compression here, extension here, and that is what we want to understand. If you have extension here, why is compression happening here? They're not like part of two different places. It's the same place. So here is a model that was given by this Wang et al. Right. So what did they argue? As you can see here, they were thinking that this is driven by gravity. So in other words, the earthquake that you're seeing is a consequence of gravity. In other words, there's something very slippery, just like a landslide. There's a slippery surface, everything is going on slipping on that. Right? That was a model that was given by Sattel and Sandel. This is called the gravity-driven deformation. The problem with that is that the earthquake was about 13 kilometers down. So gravity, 13 kilometers down gravity working, it's like something, for a landslide to occur at that depth is a bit strange. Okay? So that's one part where it's very great depth. It shouldn't be happening at that, right? And so there was another like this model, which was in 2017, one of my colleagues from Singapore. He published this paper where he's saying that there is actually, there's a basement again, but that's not shale, there is a fault at the base, okay? Not shale. Therefore, this is going to create a fault, as you see it. So because of that, you got this localized, definitely normal faulting here, but actually it has to be a thrust. In a big scale, okay? It's a thrust, but this is localized. And that makes sense offshore, because we have thrust, we have huge thrust there, and that makes sense, okay? And then, they also said that there's a basement here, or it can be just a deformation which was driven by the granite that we have there, right? We have a huge granite there, because of the weight of that, it must have slipped very localized, right? So these are the models that we think about. And I feel out of these three models, this model makes more sense compared to these two models, right? But we are still working on trying to understand more about it, and I'll show you my work, and then you'll see which model makes sense. So this is from the, this is what we call this geological map, and then I'll take you through this topographic analysis. So geological map, as you see, there are a lot of faults here, see? You got a lot of data here. Why? This is mainly coming from industry, and that's why they have released it here. They're not releasing it here much. And again, there are a lot of thrusts here, but we see normal faulting here. There are some faults which have been put here, so I don't trust all these faults. Why? Because when I put this image on top of the satellite image, it doesn't work. They're not where the faults are. We can easily see the topographic breaks, right? Therefore, this map is not, I can't trust it, but I have to present there's no other map which is available. Okay, you have to use something, but don't trust these faults. So this is a satellite image. This is uninterpreted, right? So what do you see here? You can easily see this is very easy. Like for example, this ridge here is exactly same ridge here. So what has happened? This was exactly here and has been taken out. So what you see down there is nothing but strike slip fault. It's a dextral strike slip fault, right? So this is being displaced along this. Very, very clean and clear example of dextral strike slip fault. Same thing here. Look at this river. Comes here and the river dances here. You have to see why is it doing that? Why is it going this way? And there is a reason for that, right? Same thing here. And this one is opposite. Why? Because it follows the fault, but the actual fault, the displacement on the fault is dextral. It's a dextral strike slip fault. Very, very clean and clear. So if you make, you see, I have it here. So if you make a model on this, you can make two models, right? There can be two possibilities. The possibility that I have taken is the one with normal faulting. Okay, so I think that this is a strike slip fault with a component of normal faulting. It's not pure strike slip. Same thing we have seen for everywhere. Wherever you go, you pick any rock in the center of the Borneo, you're going to end up with a strike slip fault. They are everywhere. So here's another example, as you can see here, very, very clear example of strike slip fault. So this is the same model as it's told earlier. So here, now look at this. This is a very interesting example where two faults interact. What will happen? When you have two cuts, you cut your cake like this, and here, what you end up is a pizza-shaped thing that you can have this diametric region. So what it means is that you got two faults interacting. One fault is dextral, other is sinistral. This is called a typical box faulting, and again it is there. So you can see it easily. So that's the model that I put on. Out of the two possibilities, which way it is tipping, and this is how it is before and after. Okay, same thing as I said. You can go anywhere you find the same stuff. Now this is interesting. This is the very you can see this river. This river has abruptly turned left lateral, abruptly, right? Rivers. Now remember this: rivers are blind. How do they know where to go? They take what? Most of the time they will use slope, right? But how will they be guided by? You have to go straight line. They don't have a GPS, right? So how do they know that go straight line? Most of the time, when a river is straight, you have to keep in mind that it's a fault. Okay, and we have seen so many examples like that. The same thing here in Borneo, as I said, wherever you go, you see rivers very straight lines because they are following most of the time. They're guided by faults. And here is another example showing it's a river. This one is the fault, and this say sinistral. Look here, that's 22 kilometers per hour. Okay, so this is the model that we put because we have to make which way it is dipping, right? And based on the topography, this one is actually dipping this side. Okay, if it is a cross with a component, but I don't want to go into the details of that. But the reality is that this fault, this slides the fault. Okay, same thing here is showing you the view, like the magnified view of the same thing. This is up and that's down, and then based on that you know what type of fault it is. Okay, same thing here. You can see clearly, it's very clear examples of fault strikes. Okay, so in the nutshell, what does it tell you? It tells you that there are strikes. This is sinistral, and that is dextral. Okay, now the question that you may ask is, how do I know whether these faults are active or not? Because most of the time what you see here is actually this mostly cutting very old rocks, these Miocene rocks, right? But how do you know that these are young? Now the first question we have established that there are strike-slip faults which are like both ways, right? The dextral and sinistral. And another example where this fault actually cuts through a volcano. So I have a very nice example somewhere here, which is actually a fault cutting through a volcano. And the volcano is Pleoplasticine. It's young, okay? It's clearly indicating that it's active. So there's no doubt about it, and we've already published it, okay? So the faults that you see here are active. Again, solidifying the image that we have shown you earlier, that fault, if you remember, that strike-slip fault, which was in the central Borneo, exactly strike-slip. So it exactly fits what we have seen through the image, and they are active. So, going back to the question about the earthquakes about occurring in an area which is surrounded by which is not part of the plate margins, but at the center of the plate, you go to the bush. Bush occurred in 2001. It killed 13,000 people. Where did it occur? Here, in Gujarat, at the center. Now, if they are stable, what happened here? So, we should not remain in that thing. Stable parts of the world do occur, earthquakes occur, and as I said, this is 13,000 people. Just after this earthquake, whole of the India actually revamped the way they were teaching seismology and also how the public education, and they did, this really kick-started most of the campaign in India. Okay, so therefore we should not. Let's say that we can't guarantee you that earthquake will be tomorrow. No geologist can guarantee that with all more than 250 years of experience working in earthquakes. That when it started, we do not have. We have no idea like when Earth is going to hit, but we will tell you that this area is active. Okay, it can be this possibility. Therefore, the best way is to prepare for one. It doesn't cost much. Okay, so if it was to snag, just use it.